So let's continue on. We're going to get into more fundamentals like voltage, current, power, and energy. We're also going to look at unit prefixes in today's lecture. And so let's bring up, where did we stop last time? Not this one. This one, periodic functions. And we are in one. Okay. Functions derivative, infinite integral. All right. So the most common two terminal devices, we divide it into sources and loads. Switches are used for control. Let's see, did we? I thought we already looked at this. Okay. All right, so we have any device that receives energy from a source, or well, any device that supplies energy is a source. Any device that receives and consumes energy is a load. So broadly classified, we have sources and we have loads. Power supplies are sources, and everything else pretty much is a load. Okay. There is one exception, which is a rechargeable battery. And a rechargeable battery can act as a source as well as a load. So if you're charging a battery, then the battery is receiving energy, it's receiving power. So it's behaving as a load. But once you disconnect it, now the battery is supplying energy. And so now it's a source. So that's like broad classification of electrical components. Okay. All right. So we have digital multimeters nowadays to make our jobs easier. But when the first meters came out, they were like bulky devices. They weighed quite a few pounds to 4 or 5 pounds. We still had some of those in this building. We used them for actual experiments in the lab. Okay, those are analog multimeters, came with a dial. And so the earlier symbol of a meter used to be a circle with an arrow at an angle that would represent the dial that would be present on a analog device. Okay, and so it would be something like that. So if you see a symbol like this, it means it is a measurement meter. It's a measurement meter. Now, depending on the quantity that it measures, we can have a voltmeter, an ammeter, or a ohm meter. All three of the names come from the fact that they are the units for the quantities being measured. If you measure voltage, it's a voltmeter. If you measure current, it's an ammeter or ampere meter, to use its full technical name, and an ohm meter, meaning measuring resistance. If you have a meter that can measure all of those quantities, it can now take multiple measurements, or it can measure multiple quantities. Hence, it is known as a multimeter or a multimeter. And then came along digital meters. So it became a digital multimeter, or DMM for short. And so in the lab benches in this classroom, we can see there are benchtop multimeters that can measure everything: voltage, current, resistance, capacitance, diodes. Some can even perform transistor measurements. Okay. Nowadays, digital multimeters, even the basic handheld ones, can take all of these measurements. Right. And if you've already performed experiments in 145, you'll hopefully learn how to use these meters. All right. So no matter what field of engineering we are working with, or for that matter, just any scientific field we are working in, we have to deal with a wide variation in the sizes of the quantities. Um, it could be from the very, very large to the very, very small. So we use unit prefixes. We use unit prefixes to indicate the size of these quantities. Okay. SI stands for International Standard or International System of Units. So these are known as unit prefixes. Some of them we use without any knowledge or any scientific knowledge in everyday life, right? Um, digital storage in our mobile devices, in our laptops, in our desktops, the operating frequencies, again, of the processor systems, the AM and FM broadcasting stations, our dual band wireless routers. They all have frequencies and quantities that we use with a unit prefix in front of it. So previously, it used to be that there was only one single band on your wireless router because that was the frequency band that was allocated by the government for consumer usage. And then a few years later, they opened up a second frequency spectrum. So now there's a proliferation, or actually, they are now much more common. Previously, we only used to have one band. Now we have like dual band wireless routers. So, anyone recall what's the frequency on those bands of your wireless routers? Anyone? That is correct, 2.4 gigahertz. So a few years ago, the FCC, meaning the government, opened up the 2.4 gigahertz frequency spectrum for consumer devices. And so companies started selling consumer devices like not wireless phones, cordless phones, which were connected to actual landlines. So it's kind of before the days of the mobile phones. Anyone ever use a cordless phone before? Right. So those cordless phones would have a receiver. That receiver would plug into the wall. That would become a transmitting station, and you'd have a cordless handset. You could roam around, kind of like Bluetooth. You could roam around a certain area depending on the strength of the transmitted signal. And those would operate on a 2.4 gigahertz frequency spectrum. Frequency spectrum, by the way, is tightly controlled by every single government in their own countries. Okay. It's very expensive. It's a precious resource. And the government auctions off the right to use a particular frequency every few years. So all of these transmitting television stations, cell phone companies, Sprint, well, Sprint no longer merged with T-Mobile, but T-Mobile, Verizon, AT&T, they all bid in an auction and buy the right to use these frequencies. Once they purchase the rights, no one else is allowed to use those frequencies. And that is the reason why you cannot use one. Well, this is one of the reasons why we cannot use one mobile device from one company to another. They lock it down. They lock it down so it only works with their own frequencies. All right. Anytime we tune a radio station, we use our radio and tune it to like a 640 AM or a 101.7 FM. We are tuning to the frequency at which the signal is being broadcast. So the signal is broadcast at that station. I mean, 640 AM means that radio station is broadcasting at a frequency of 640 kilohertz. So when we set our frequency of our radios or our devices to 640, there is no other station that should be heard at 640. Otherwise, that is known as interference. Anyway, so we are dealing with a wide range of values, and so we have a wide range of unit prefixes that we use. And on the following slide, I have a comprehensive list that I want every student to memorize. I'm going to ask this with closed book, closed notes on a quiz. Not really. Even I don't have these memorized. I only memorize, well, not memorize, but we use the middle of the table widely, right? And so we are familiar with the middle of the table. And that's about it. So on the left, we have the multipliers. On the right, I say it's not technically known as the divider, but I tell them it's the divider. They're both multipliers, obviously. But we are familiar with the middle of the table. We are familiar with kilo. We are familiar with mega, um, tera, mega, giga, tera. We use it for frequency. We use it for storage, right? We have like 15 gigabytes of data or 15 gigabytes of RAM in my device. Or I might have like 1 terabyte of a hard drive or 1 terabyte SSD storage in my laptop. And so we are talking about 10⁶, 10⁹, 10⁻². The first computer that I had as a student was in 1999 in India. And I think it had 128 MB of RAM and a 4.3 GB hard drive. And that was huge at the time. It's like, that's a ton of space. What am I going to do with all this space? Use MP3 files, listen to songs. Long time ago. Nowadays, 4 GB is not even the minimum size of the RAM memory inside our systems. Anyway, so we are familiar with these three right here. On the right side, we're pretty much familiar with these right here. Right? We have milli, which is 10⁻⁻3. We have micro, 10⁻⁻6. Nano, 10⁻⁹. Nano, by the way, is in vogue in the last few years. Like everything's about nanotechnology and nanoelectronics and stuff like that. To give you an idea on both sides of the scale that we're talking about, we're all familiar with a millimeter, right? Millimeter, we use scales, we use rulers, so we know what centimeters are. We have an idea of what 1 millimeter is. If you take 1 millimeter and you divide it into 1,000 parts, that gives you 1 micro. 1 micro is also known as micron. Okay, so if I use micron, that's what I mean. It's 1 micrometer. So 1 micron is 1 micrometer. And that's where the name microchip comes from. The reason it's called microchips, it's because they were chips that were size of micro scale. Brand new installation doesn't work. Anyway, all right. So that's where the name microchip comes from. Like chips are cut from actual wafers, and the feature sizes were in micron scale, hence microchips. There's an actual company with the name of Micron. Ever hear of that? Right? Semiconductor company. Then if you take 1 micron and divide it into further 1,000 parts, that is 1 nanometer. Okay? It's so small we can't even visualize in my head, even though my area of specialty is micro nanotechnology. Right? The feature sizes of the current state-of-the-art microchips is about 3 to 4 nanometers. We're talking about feature sizes that small. Okay, this is the reason why we use those. As pertains to your study specifically to this course, you will work with resistors, you'll work with capacitors, you'll work with inductors, you'll study about those devices, right? So the capacitors and inductors that we use in everyday life, in electrical devices and in electronic devices, they are on the order of milli and micro. Okay, even milli and micro are considered to be large. So capacitors, inductors are typically smaller than milli or micro, right? So this is the typical range for inductors and capacitors. Resistors, pretty much on this side. Resistors are typically in the kilo ohms and mega ohms range. give you an idea of how big these numbers are, let's use the concept of time. 10 raised to 6 or mega is a million. Right? Nowadays, the trillions of dollars gets thrown around like it's nothing. Right? So how much do you think is 1 million seconds? In days, weeks, months, years? Wild guess. Several months, okay. That's a decent guess. Anyone? No one else has any idea? Well, not idea, but want to take a guess? 5 years, that's another good one. 2.5. 2.5. It is less than 12 days. It's 11.71 days. So comparatively, how much do you think is 1 billion seconds? Any wild guesses? 3 years is good. 10 years is also good. 2.5 years again. 20 years. You're looking it up. It's more than 31 years. That is the difference between a millionaire and a billionaire. So 1 million seconds, less than 12 days. If you're a millionaire, you had $1 million in cash with you and you spent $1 every second, you run out in less than 12 days, less than 2 weeks. A billionaire could spend could spend $1 every single second of your lives, would not run out for another 30 years. And a trillion, well, trillion is easy now. 31,000 years. The current federal budget deficit, meaning the debt that is owed by the country, is how much? Anyone know? It's over $30 trillion. 30 trillion. So 30 times 31,000 years, you pay back $1 every second, to still take about, what, 90,000 years for the country to pay off the debt. Anyway, we don't want to go sidetrack or anything like that. It's just that it's financial information that you all should be aware of. This is the world that you'll be inheriting, or which we have inherited and which you'll inherit, right? So that's something to think about. Anyway, all right, let's get back to our current, voltage, power, energy. How do they all relate, right? Charge and energy are fundamental, okay? Energy is governed by the law of conservation of energy, first law of thermodynamics. Energy can never be created or destroyed. As far as our understanding goes, it's always converted from one form to another. Okay, it's always converted from one form to another. Charge is also a fundamental quantity. We are all familiar with the structure of the atom. The smallest particle that we can think, the smallest structure that physics and science knows in this day and age as of today. Atom is comprised of a nucleus which has positively charged protons, neutrons in the nucleus, and it has negatively charged electrons orbiting that nucleus. So charge is fundamental. Nucleus is tightly bound. The protons and the neutrons are tightly bound within the nucleus. Electrons are free to move around. When electrons move from atom to atom or from out of their structure, they leave that atom and they're free to move around the material. They carry their charge with them. When they carry the charge with them, they can impart certain energy. They can transfer certain energy. This flow of charge, or more technically, the rate of flow of this charge is defined as electric current. So I is the rate of flow of charge, Q over T, or delta Q over delta T. Change in charge with respect to time. But technically, it's to define that the rate at which charge flows. Okay. Time rate derivative of charge, dq over dt. A unit for current I is amperes, named after ampere. In the same manner, if we are moving a charge, it requires some energy. That energy can be from external sources, can be thermal energy, but that amount of energy needed to move the charge from one place to another is defined as the voltage. Okay, and so that voltage has units of volts named after volta. More technically, it's the work done to move charge from one place to another. So delta W over delta Q. The W is lowercase w, stands for anyone? That's work being done, yes. But just in technical terms, what does it stand for? Energy, unit of joules. Energy, of course, again, is defined as the work that's being done. So all right, let's take a pause. Let me know if anyone has any questions. Yes. Question being asked is voltage dependent on current? I would say they are both dependent on each other. If there's current flowing, then it depends on the voltage, and the voltage that appears across a component also depends on the current. Current cannot flow without there being voltage. But voltage can be present in an open circuit where there is no current flowing. An example would be our power outlets. Power outlets, again, do not have any current that's flowing, not until we actually connect a load to the power outlet. Once we connect a load to the power outlet, then the circuit connection is complete, then electric current will start flowing. But if we measure the voltage of a power outlet, we will say it is a live power outlet, and there is voltage that is available at the power outlet. But in general, if a circuit is powered, you're applying a voltage, then the current would be related to the voltage. If you apply current, then the voltage would be related to the current. They're both related to each other, yes. Right. Okay. All right, power. Power is the rate at which work is done. Hence, delta W over delta T. That means the time rate derivative of the energy, dW over dt. The rate at which work is done, or the rate at which the energy is transferred. Rate at which energy is transferred. Okay. In pure electrical terms, I can simply state Actually, let me write it out here. That power P is the product of voltage and current. P equals VI. Okay, P equals VI, or P equals IV. Either ways. Power, electrical power is the product of the voltage and the current. That's where we get it from. Derivation, the small derivation is shown right here. It's dW over dt, rate at which the work is done. We can break that up by taking the derivative of the energy with respect to charge, dW over dQ, and then dQ over dt. Well, by the strict definition of voltage and current, those are turned out to be V and I, voltage and current. And hence power at any given point in time is the product of voltage and current. All right, so unit for power is watts, volts times amps. Okay, volts times amps. Let's see. What happened here? What in the world? Okay. We talked about sources and loads, right? Sources and loads. When it comes to energy and power, what defines a source? As the name suggests, yes. Power supplies, yes. And so a source will supply power and energy. And a load will receive or consume power and energy. Okay. A source will supply power and energy, and a load will consume power and energy. This is very important. If you look at your laptop adapter chargers, mobile phone chargers, what does it say on there? 19 volts DC output, right? It's supplying, it's a power supply. It's supplying some energy and power to your device. Mobile phone charger might say 5 volts. But have you ever seen a device where it says minus 5 volts or minus 19 volts? No. But when we are dealing with these mathematically, in order for us humans to balance out our equations, we put a minus sign in front of any device that supplies energy and power. Otherwise, our equations would never balance out. So if it's a supply, or if it's a source, the equation for power would be P equals minus VI. When it is a load, P equals plus VI. The plus and minus, again, is only for us humans to differentiate and for us to be able to balance out our mathematical equations. We would never say my laptop adapter is minus 20 watts. We would simply state it's 20-watt charger. But if you were to write it mathematically, you would need to have minus 20 watts from the adapter, and our device would be consuming plus 20 watts. Otherwise, you would never get zero, right? It must balance out. It must always go to zero. So this is a very small but very important concept, right? So we'll end class here today. We'll pick up here again on Wednesday. See ya. Please review the slides and have your questions ready if you have some for the beginning of next class.